the different equations that we were working on last week from our impulse and momentum notes. So the equations that we're working with are much simpler than kinematics. So I hope that we can remember some of these. The first one is momentum. Does anyone remember what momentum is equal to?
Mass times velocity.
Excellent. Mass times velocity, right? We got three symbols. Hopefully we can remember these. You'll have access to equations on the test, sure, but it is always more helpful to just have the equation with you, especially when it's relatively simple like this one. All right. The next one is impulse. What is impulse equal to?
Force times time.
Excellent. Yeah, it is the force applied over a period of time. And then how do they relate to one another? We mentioned an equation called the impulse momentum theorem.
The change in momentum is equal to the impulse?
Yeah. Impulse is equal to change in momentum. Or we can write it out with the different pieces. So it's force times time is equal to mass times change in velocity. We're going to be working with all of these equations today. And so if you don't have them down on your notes or they're not with you, pull them out, write these down really quickly, because these are the ones that we want to focus on. So when we're talking about physics not caring about our feelings, it wants to care about these equations, how the world is operating. So when we want to know about momentum, it's not how much momentum we feel is there, it's how much momentum there is. If we're looking at how impulse compares to change in momentum, if I know the change in momentum, I know the impulse, right? It's not how much we feel is there or what our intuition is telling us. That's another way to think about it, is our intuition. What's the initial thought that comes to our mind? We want to test out those thoughts with the equations, with the concepts at hand. I'll give us another moment to write it down, and then we'll move on to the practice problems for today. Okay. So we're going to be working on this worksheet that I posted to the Google Classroom. It is a PDF, so I didn't make your own copy for you. Instead, you can either translate it into a Google Doc, or you can just write down your answers on a separate sheet of paper. Either or works for me. Okay. Give you another moment to finish that up. Donkey Kong. I'll be right back. All right. So the first thing that we're working on is a little bit of review from kinematics, just to get our brain started. So we know the different masses of our football players here. They're running down the line. There's these ticker tape patterns, right? So each dot or each space represents that a second has passed. So in between here and here, here and here, here and here, 1 second has gone by. So we know that the halfback is moving the fastest because the largest distance has been traveled in 1 second versus our lineman. But we don't know how fast they're moving. We do know that the lineman's velocity is 3 meters per second, and we want to find the tight end's velocity. So if the velocity is constant, testing your memory one more time, does anyone remember the equation for velocity? The simple equation.
Distance over time.
Yeah. Good work, Tristan. Distance over time. Okay. So we know all the times, right? I know the, like that takes 3 seconds, this takes 4 seconds, stuff like that. But I don't know the distance. I don't know what the scale is here. So if I want to find the velocity of the tight end, I can't just do it on its own because I don't have distance, even though I know the times to the different dots. Instead, what I can do is I can use the lineman numbers, because at this position here, they are at the same position, right? But it took them different amount of times to get there. So I can rearrange this equation so that distance is equal to velocity times time. And once I have this number, I can plug it into this equation. So using the lineman's number, the velocity of the lineman, how many seconds does it take him to get to the position?
2.
Yeah, it's going to take him 2 seconds to get there. So I'll do the math because it's super simple, right? 3 meters per second times 2 gets us a distance of 6. Plug it into this equation, it only takes the tight end 1 second there. So 6 meters over 1 second, 6 meters per second. 6. So a little complicated in the problem solving aspect, but not too bad with our calculations. All right. So we're going to do the same thing for the next one, but notice that the halfback isn't at the same position, right? Some distance farther. So we will need to find a new position where the tight end and the halfback are at the same place, which is right here. So it takes the tight end 3 seconds to get here, halfback 2 seconds. And then we're just going to do the same steps, but with different numbers. So we'll find the distance that the tight end travels in 3 seconds and the velocity of the halfback at the same position. So it's 6 meters per second times the time of 3 seconds, which gets us 18 meters. And we have 18 meters over 2 seconds. 18 divided by 2 gives us the 9. Any questions on this? Anything that's confusing? I could go over one more time, describe in more detail. Okay. All right. The next one is the part that I want you to try out, and that is which player has the greatest momentum and how much momentum does he have? When you have the answer, send it to me as a private message. I'll give you about a minute. Make sure to also send me the value. How large is the momentum? All right. I think we are on track here. So the multiplication should be pretty simple, right? It's mass times velocity, what we were just doing before with those equations. So 9 times 80 is going to give us 720, larger than 600, larger than 360. So it's going to be the halfback. So even though he has the least amount of mass, right, we would expect the one that has more mass to have more more momentum. And that is true if they all had the same velocity, which they don't. So because the halfback's velocity is 3 times as large, and the lineman's mass isn't, what would be 3 times? 240 kilograms? Oh my gosh, that would be a large man. I'm like 70 kilograms. So yeah, the halfback's already a pretty heavy dude. So halfback, 720 is our answer for number 1. Okay. Now what I want you to do is I want you to interact with the page a little bit because you are able to annotate on my page if you want to. I want you to do what it says here, indicate on the dot diagram, not yet, but when I give you the go ahead, I want you to draw your arrow on the approximate location at which the fullback, defensive back collision occurs, right? So there's this collision that happens. We have another dot diagram. So you should be able to annotate on my page if you go to options and click on annotate, but don't do it just yet. I'll let you know in like 10 seconds. Think about where on here you think the collision occurs, right? Point to the spot. Take another 10 seconds. Think about it. Where do you think it's going to go? All right. Draw your arrow. Where do you think the collision is going to occur? Okay. So see, we're drawing a lot of lines kind of in this region here, which is great. We want to draw the arrow at the point where the spaces get smaller. That means that our person is accelerating. There's a net force on them. They're slowing down, which is what happens in a tackle or collision, right? What I want you to now say is send me a message. Which direction is that force acting, right or left? If it's going to the left, you're telling me that the force is against the motion. If it's going to the right, it's going with the motion. Send me your best guess. What direction do you think the force is acting on our fullback? Sweet. So a couple of us are split on left or right. So if we clear these drawings, we notice that from here to here, right, these kind of look similar to me, but then it starts to get smaller. Because the spacing is getting smaller, we are losing velocity, right? We're not traveling as far each second. That means that we are slowing down. The force is against motion, right? This would be like friction. Friction resists that motion. Actually, we would call it resisting slipping. So in this case, the force is against motion. It's going to the left. And that is because we are losing velocity. If you're losing velocity, you have a negative acceleration. You have an opposite force to the motion. Mateo, could you tell me the answer to the next question about momentum? What happens to the momentum?
The momentum reduces.
Yeah, we, using the same terminology, we would say we lose momentum, right? Because we lose velocity. Cool. So this is the review piece. And we're doing a little bit of momentum here. The next part is where we need to trust in the equations that we have, not necessarily in what we feel should be true. So we have two cars. They have the same mass, and they start with the same initial velocity. And they both come to the same final velocity, right? They've come to a stop, but different lengths of time So the dot diagram's right. They're telling you the motion. So take your best guess for which one has the greatest acceleration. Send me a private message with your answer. Maybe think about which one's going to have to push down on the brake harder. Okay. So first off, we need to remember what defines acceleration. So when we first learned about it, what lets us know when something is accelerating? Anybody remember from long, long ago?
The changing of the velocity over the time.
Yeah. So acceleration is defined as change in velocity over the change in time. So we should first identify that both have the same change in velocity, right? They both start at whatever and they end at the same speed. Not necessarily the same time, but they end at the same speed, which is 0. So the delta V is equal. What about the change in time? One ends faster, one ends slower, one takes more time. So when we think about division, this is kind of a math part, is when we're dividing by a number, the smaller the number we divide by, the larger value we get. So if I divide by 4, right, 1 over 4 is less than 1 over 2. So the smaller the number I divide by, the larger the actual value, the total value. So I want to divide by the smaller number, and that's going to be the least amount of time, which is car A. If we think about pushing on the brakes, right? If I slam down on my brakes, I have a larger acceleration. I'm going to stop faster. If I just lightly press on the brakes, right, I'm going to slow down over a great amount of time. I'm not going to accelerate, change my velocity very quickly. Cool. I got a question in the chat asking, wouldn't that be negative acceleration, which car A has more of, making car B have a greater acceleration? So you're thinking about the sign here. I'm just thinking about maybe the scalar value or just the larger absolute value of the acceleration. I'm not necessarily considering direction here in the question. All right. Now, next problem. Next question here. Which one experiences the greater change in momentum? Is it going to be A? Is it going to be B? Is there another answer? Focus on the equation. Think about how the two different values might be different or the same. When you have your answer, send me a message in the chat. All right. So we're again a little inconsistent, which is okay. We're starting off. This is practice. We want to figure things out. So first off, before we get to the answer then, what is change in momentum equal to? What did we write down?
The mass times the change in velocity.
Yeah. Mass times the change in velocity. So we want to compare the two values. Do they have the same mass or different masses? One bigger than another.
They have the same mass.
Same mass. So this doesn't really help us, right? Not super important for determining which one's going to have more. What about their changes in velocity?
They both experience the same change in velocity.
Right? Notice the same spacing here, same initial velocity, and they both come to a stop. The time it takes to come to the stop is different, but we don't really care. We care about what their change in velocity is, and the change in velocity is the same. Notice it's not change in velocity over change in time here, right? The time element's not important. So the answer is neither or the same. Neither / same. Because the two components that make up change in momentum, well, they're the same. Okay. Questions on this? We are a little inconsistent here. Anything I need to clarify? Also, I'm getting people not committing to their answers. I would like you to commit to your answer. No question marks, please. It's a guess. It's fine. It's fine if we get it wrong. We're figuring it out. Caitlin, did you have something you were going to say? I saw you on mute for a moment. Okay. All right. Trust in the equations that we have, right? So what about impulse? Which one's going to have a greater impulse? Is it going to be AB, or is it going to be this other answer, neither / the same? Think about the equations. Okay. We're much more consistent on this one. Impulse is equal to the change in momentum. Now, the forces and the times that make up impulse are going to be different, but we want to focus on the equation where it says impulse is equal to the change in momentum. So their values, again, are going to be the same. Because the impulses are equal to the changes in momentum, and because those things are the same, then impulse is going to be the same again. Now, impulse is made of forces and times. So knowing this, and knowing that both of the impulses are the same, so the impulse for car A and the impulse for car B are the same. But what about the force? There's also a different way to think about this too, if you're creative. Send me a message in the chat when you think you have the answer. Take a guess. I would encourage you to think about jumping into the lake, right? Like when we were talking about, you could either jump into a lake that's filled with water or doesn't have water. All right. We're split. Either car A or car B. So the time element here is important because it has to equal the same thing, but we know that the times aren't equal. So we know that the time for car A is small and the time to get car B to stop is larger. Exaggerating the times here a bit. So if I want to balance these out, since time is bigger here, force is going to be smaller for car B. Since time is smaller here, force has to be larger. So if we want to know which one experiences the greatest force or the greater force, it's going to be car A. The other way we can think about this is we already talked about acceleration, and we know that force is equal to mass times acceleration. So if car A has a greater acceleration, then it's going to have a greater force since mass is the same for both of them. So there's two ways to think about this one. Questions on these problems? Anything that you want me to review a little bit more before we end? Okay. Now, let's say that you do have a question. I'm going to actually, no, I'll keep going. Let's say you do have a question for later, and what you're going to do is you're going to go to the classroom and sign up for office hours. Under essential materials, which you guys haven't looked at since the beginning of the school year, I had these survey and syllabus. I've now added this document called important class information. It has the Zoom link here. So I'm no longer going to be posting it to the Google Classroom. Instead, it's just going to be in the in this document. So if you want to lift that and put it in like some master copy that has all the Zoom links for all your classes, feel free to do that. But I'm not going to be posting it to the Google Classroom. The way that you'll know that if there's classes by the weekly rollout, right? You'll always have classes on Tuesday, but I'll let you know if the top row of the weekly rollout is empty for Friday, then you won't have a Zoom class. And then if you want that help, like I was talking about, you're going to click on this link to go to calendly.com. And now it's going to show up with a calendar, and you can sign up for office hours. So if you want to sign up for office hours on Monday, right, you finished this worksheet, but you were a little confused at number 5, you can sign up for office hours at 1 o'clock. And then I will know that you will be there. And that way I can get grading done and do some planning, and it should be a little bit easier for me to be up to snuff with class and get that stuff in so that you guys aren't confused about, wait, Mr. Z, did you grade the thing? So hopefully it should be in a little bit faster, okay? But that's how you get there. You go to essential materials, important class information, click on the link, and sign up.